peculiar patch of Earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces.
Good morning. It's a pleasure to have the short course, Semiconductor Device Characterization, a quick tutorial, sponsored by Keysight Technologies. The course will be divided in two parts. The first one from 8:30 to 9:30 with about 1 hour. At the end of the first part, we will have a 15 minutes break. The second part starts at 9:45. At the end of the tutorial, Alan Wadsworth and Teja Kothamasu from Keysight will be available to answer your questions. The course slides and supporting documents will be available at the link that I'm going to type in the chat soon. The tutorial will be given by Alan Wadsworth. Alan Wadsworth is the Americas Region Business Development Manager for Precision and Power Products at Keysight Technologies. He has over 30 years of industry experience in both semiconductor design and test, and is the author of Keysight's 277 pages parametric measurement handbook. Alan has both Bachelor and Masters of Science degrees in electrical engineering from the Massachusetts Institute of Technologies, MIT, and an MBA from Santa Clara University. Please enjoy the short course.
Hi, welcome everyone. My name is Alan Wadsworth. I'm the Business Development Manager for Precision and Power Products here at Keysight Technologies for the Americas region. And today we're going to give you a quick tutorial on semiconductor device characterization. Hopefully you'll find it interesting. I will be covering a lot of material fairly fast at times, but don't worry, I'll give you a resource at the end that you can download if you want to get more information on anything that I talk about today. Also, at the end, we will have a live Q&A session. So along the way, if you have some questions, why don't you make some notes, and then we'll hopefully get to them when we get to the Q&A. This class is divided into two parts. So in the first part, I'm going to cover the subjects shown here, which I'm not going to go through and read every one of them because I think you can read them yourselves. Basically, I'll just initially talk a little bit about some of the basics of measurement and semiconductor test. I'm going to talk about SMUs and how to make IV measurements, and then later on cover capacitance measurements. And then we're going to take about a maybe 10-minute or so break, and I'll go on in the second part and cover some more advanced topics. So what is semiconductor parametric test? Well, unlike functional test, where you're measuring basically the performance of a finished product, in parametric test, we're actually measuring the devices and the process itself on which the semiconductor device is made. So we're testing the device parameters. And to do this, of course, we actually have to perform both IV, current voltage, and CV, capacitance voltage types of measurements. Basically, in parametric tests, we actually only test 4 types of devices. We have resistors, capacitors, diodes, and transistors. Really, that's it. Some of the tests, however, can be actually quite complicated. Now, as you can see there on the left, there's some sort of typical IV measurement examples, some generic IV measurement curves in the middle, and we use these to extract the types of very important, actually, device parameters shown on the right there: threshold voltage, transconductance, on resistance, breakdown leakage currents, etc. Before I jump into starting talking about IV characterization, I wanted to spend a couple slides just going over some measurement basics because a lot of times what I find out is people get sometimes a little confused between the terms accuracy, repeatability, and resolution. So before we go on, I just want to make sure that everybody understands exactly what I mean when I talk about those terms. So what are accuracy and repeatability? So accuracy is the conformity of a measured or calculated quantity to its actual or true value as determined by some sort of standard. And again, there's many organizations that deal with standards in various countries. So I'm not going to go into that. Repeatability, or it's also called precision, is the degree to which a repeated measurements, I should say, or calculations show the same or similar results. It's important to understand that there's no innate correlation between these two things. So I like this bullseye target kind of analogy here. Again, you can see in the lower right there, you can have a situation where you've got high accuracy, but low repeatability because the points are not close together. You can also have on the right there a case where you've got low accuracy, but very high repeatability, where you've got these points that are very close together, but they're very far away from their actual or true value. In parametric tests, really one of the most important parameters is the resolution of the equipment that we're using. And resolution is simply the smallest change in data that an instrument can display. The way I sometimes like to look at this or think about this is because remember, we're converting an analog signal to a digital value of some sort of a number, right? And you can really consider that in terms of an analog to digital converter. And the accuracy of that really is determined by the number of bits in the D to A converter as shown in this sort of simplified circuit diagram here. And again, for example, if you have 20 bits of resolution, that represents roughly the ability to distinguish one part in 2 to the 20th power, or about a million. So again, this is a very important parameter for parametric test. In the next section here, I'm going to be talking about source measure units, or SMUs, for parametric test, because these SMUs are a little bit different than the ones you might be used to if you've used SMUs for other applications, like say maybe battery drain testing, things like that. These do have some special needs and special characteristics, kind of unique for parametric test. So anyway, I'll cover all those in the following slides. In parametric tests, the fundamental unit that we, or a module that we use to measure things, is the source measure unit, or SMU. And as the name implies, it can both source current or voltage, and at the same time, it can measure actually both current and voltage, independent of what it's sourcing. These typically have very low voltage and low current resolution, as I just talked about. And as you can see here, they're also, in parametric test world, typically 4-quadrant devices. We can actually source and sync current in all 4 quadrants shown there. And that's important because we not only want to supply current with positive current and voltage, but sometimes we actually want to apply a negative voltage and see like a breakdown current, which shows up as a negative current typically. So it's important to have that. Our SMUs typically also have other things I'll talk about in subsequent slides. They're triaxial outputs with active guards. They can do 4-wire or Kelvin measurements. They also typically have auto ranging, and they can also do some pulsing to prevent device self-heating. So you're, I'm sure, familiar with B and C type connectors, but you're probably not familiar with triaxial connectors unless you actually have done some parametric test work in the past with source measure units. That's basically because SMUs always use triaxial outputs because they need to measure low current. And I'll explain that a little bit better maybe in the next slide, but because there's as you can see in this simplified circuit at the bottom, there's kind of a follower circuit. So whatever we're forcing The driven guard, which that is the center conductor there, it's surrounding the force line, and then the common, of course, the ground is on the outside. Basically, because that guard's always at the same potential as the force line, there can't ever be any current between the two. So there's no leakage, and that allows us to get very low level measurements like below a nanoamp. We can go down to femtoamp or even sub femtoamp measurements using triaxial connections and cables. So this slide shows kind of one example of how to think about the reason we use triaxial cables. So you can see at the top there, if we had say 100 volts going through a BNC cable, well, even if we had a gigaohm of resistance in the insulator going to the outer ground shield, that's still a significant amount of current that can leak out. And again, like 100 nanoamps. So if you're trying to measure very low levels of current, you obviously can't do that with a simple standard BNC cable. Whereas on the bottom, because the driven guard is kept at a potential very, very close to what we're actually driving, within maybe 1 part in a million, you actually get extremely, extremely low leakage from the triaxial cables. And again, on the right there, you can see an example of a graph, the difference between using a coaxial and a triaxial with a driven guard. So what's a 4-wire or a Kelvin measurement? Well, that's basically a measurement made that, or a measurement that we make when we want to eliminate the effects of cable resistance in our measurement. And there's typically 2 times you have that happen. For kind of low signal parametric test, if you're measuring a very small resistance, like fractions of an ohm, then typically you have to worry about this because the cables can be a significant part of that total resistance you're trying to measure. Or if you're measuring high power devices, obviously, and you're pumping amps of current through the cables, you're going to get a pretty big ohmic drop. But in essence, what you're doing when you're doing a 4-wire measurement is you're separating out the measurement lines from the force line. So as shown here, the force line at the top is forcing the current through the into the DUT. And of course, there's a resistive drop there in the cable, but it doesn't matter because the actual measurements are occurring at the bottom 2 lines there, the sense lines. And because there's no current flowing through those lines, there's no ohmic drop, and there's no, so you're measuring exactly what the DUT itself is seeing. So this is a nice little trick when you have to worry about the effects of cable resistance on your measurement. So this slide really just reemphasizes what I talked about on the previous slide. Shows a couple examples at the bottom there of a Kelvin connection versus a non-Kelvin connection, pointing out the error that gets created because of the resistive drop in the lines. But I also kind of wanted to show this because there's an actual measurement shown on the right there. And you can actually see on that ID-VD family of curves, there's obviously a very distinct difference between a measurement made with a Kelvin connection, which is giving the correct data, and the non-Kelvin connection in red, which is showing actually an erroneous measurement. And it's an error because it's measuring the resistive drop in the cables. So again, it's important for these situations to understand when you should and should not use a Kelvin measurement. Virtually all of the SMUs that we sell for parametric tests are Kelvin or 4-wire and also triaxial. So this slide kind of shows you how that all works together. This schematic is a simplified schematic of a Kelvin triaxial SMU output. And notice that in this case, the 2 lines are connected together through a resistor, which means that if I'm making a standard measurement, in other words, not a 4-wire, and I just connect up the force line, then I still have a connection to the sense circuitry internally through that resistor. But if I want to make a 4-wire or Kelvin measurement, I hook up both the sense and force lines, and of course the sense line has a direct connection then to the sense circuitry inside the SMU. So this is kind of a nice solution because you don't have to think about what you're doing with the SMU. Now some SMUs, I'll just mention, also have instead of a resistor, sometimes they use a relay. So I guess that has the advantage again if you want, you can open the relay and totally when you're making a 4-wire measurement, and you totally isolate the force and sense lines from each other. But of course, the relay has to be closed if you're not making a 4-wire measurement, because again, you've only got the force line connected. And that means basically you actually have to tell the SMU what you're doing So that's kind of the disadvantage, I guess, is that you have to tell the SMU what you're doing. It's not an automatic connection, but both types of schemes work. And again, this is just something to keep in mind. And by the way, never hook up only the sense lines to SMUs, because if there's a resistor there, then everything has to go through that resistor to get to the circuitry, and you're going to get very strange measurements. So again, if you're only making, if you're not, I should say, making a 4-wire measurement, you just want to use the force lines. Don't ever use just the sense lines. Keysight actually makes a special, what we call Kelvin triaxial cable. As you can see here in this picture, it kind of shows an example of it. It combines everything together into a single cable, as shown in the little diagram there, for sense, force, guard, and ground. It does give a little bit better low current performance. It's more compact, and of course, obviously, it's impossible to misconnect the force and sense lines. How honestly speaking, the people I see that use this mostly are people that use their equipment almost exclusively with a wafer prober, because that's the easiest way, because then the wafer prober accepts the cables, and the thing about if you want to use these types of cables, you need to make sure that whatever you're using it with accepts them, and not everything does. So again, it's just something to be aware of. These are available, and sometimes in certain situations they can be useful. SMUs have something called measurement ranging, and it shouldn't be too hard to imagine why they have this. If you think about it, obviously you have to switch in different circuits or different components to measure a very large, say, voltage or current versus a very small voltage or current. And it takes some time to do that. So as the SMU has to go through and measure different levels of voltage or current, it has to make some internal changes to its circuitry through relays and things like that. So there's actually 3 basic types of measurement ranging. There's fixed ranging, where their measurement or range always stays in the same range. There's something called limited ranging, which starts at the top of the range and then goes down to whatever limit you've specified. It won't go any lower than that. And then there's auto ranging, which will go as low as necessary to make whatever measurement you need to make. So again, in terms of speed, it should be apparent that the fastest is fixed ranging, next fastest is limited ranging, and then after that is auto ranging. So it's important to actually understand when you might want to use each type of ranging for different types of measurements that you're making. So when you're in a given measurement range, you get about 5 digits or 5 decades of accuracy below that range. So again, if you're in for example, a 10 milliamp range, you can't go down and measure, nanoamps or picoamps accurately, because you actually need to go to a lower measurement range. So you should never try to make low-level measurements in a fixed range, or even a limited range if you set the range higher than the range you actually need to be in. So it's important to understand that to make low-level measurements, you need to be in auto ranging, so that the instrument can actually go down all the way to whatever range it needs to be in to make an accurate measurement. But again, be aware that when you make auto ranged measurements, especially at very low currents, it will take a long time. So expect to see, especially at the lower part of the curve, if you're trying to make a sweep measurement, it's going to take a long time and then start to speed up, obviously, as it gets to the higher voltage or current levels. Another important parameter to understand for SMUs is that they do have at least some pulsing capability. And you can see on the right there, like for example, a spot measurement made in both DC and pulse mode, and a sweep measurement made in standard mode and pulsed mode. And again, the reason that you want to do a pulse measurement is simply to minimize the amount of time the device is on, because when it's on, it's going to generate heat and it's going to generate power. And that will actually, after a while, start to change the actual measurement results you get, because the semiconductor device, its behavior does depend on temperature. And again, on the left there, you can see the difference between a sweep, IDVD sweep made in both DC and pulse mode. So again, this can be important for general parametric tests, but it's especially important when you want to measure power devices, because they obviously have hundreds, thousands, many amps, hundreds of amps of current flowing through them. And so typically for power devices, you want to have a very small duty cycle,
Gabriel?
less than 1%, maybe a
Posso falar
fraction
com o Gabriel?
you're actually measuring. And most of the time you want to have them off so they cool down
Armado.
actual measurements. Another important parameter to understand for parametric SMUs is we typically have a compliance setting for voltage or current. And in fact, sometimes they have a power setting as well. And so they'll shut off or stop the limit out at whatever is the lowest of those values you set, for either current voltage or power. But basically, that's just there to prevent your device from getting destroyed. Because again, applying sometimes too much, current or voltage, especially if something breaks down, could destroy the device. And having the compliance setting will actually stop it from going any higher, and therefore prevent inadvertent device damage in situations. So make sure that you understand what the limits of your devices are, and that you set your compliance setting appropriately to prevent them from getting damaged. Remember when I talked about
Meu amigão, o fone
resolution?
aqui, tudo
It's very
bem?
important
Ele falou
for
que vai
parametric
mandar,
tests.
mas
It
não
is,
fez
and
reserva
it's also
ainda.
important to
Onde está o
understand
valor que vai colocar?
what how many bits, I should say, your analog to digital converter has on your SMU. Now, again, I just want to point out some parametric instruments actually have 2 analog to digital converters available. So typically, they might have a high resolution one, which is 21 or 22 bits, something very high, but it's a shared resource. And then they also sometimes have a per SMU ADC, which is, I would say, a high speed, because obviously, if you're using that with the SMU, you can go much faster, but it has probably fewer bits, maybe like 16 bits. So you lose some resolution. But again, the trade-off is speed. So if you wanted to do, for example, true parallel measurement, you can't be using the high resolution ADC because that's a shared resource. And if you want to make a true parallel measurement, having everything measure at the same time, you need to make sure that you set your equipment up such that it's using the high speed or per SMU ADC and not the centralized ADC. So I want to make sure that everybody understands the purpose of SMU integration time, what it really does. And again, integration time is there only to eliminate noise, and it does this by averaging out, it takes multiple measurements over some time period you specify, and it averages them together to eliminate noise. Now, what's the most prevalent source of noise in a lab? Typically, it's power line cycle noise from the AC voltage you're getting powering up your instruments. And that's going to be either 50 or 60 hertz, depending on what part of the world you're in. And by the way, most instruments do have a setting somewhere hidden in them to where you tell it whether it's 50 or 60 hertz. So be careful that you know about that, and check to make sure it matches your country's spec. But in any case, typically we call short integration time anything less than a power line cycle. Medium is exactly 1 power line cycle, and long integration is something that goes on for multiple power line cycles. And how long you have to integrate something depends on, really the noise of your environment, and a lot of times also the level of the signal you're trying to measure. Lower level signals typically require longer integration times. It does not have an effect on the resolution. That's determined by, the setting, whether you're in, short, limited, or auto ranging. That, because to make an accurate measurement, again, you have to be in a low enough range to make that measurement. So don't confuse that this with the ranging. That's a totally separate issue. But again, it's important to understand how to use it and when to use it, because it is an important parameter for certain types of low level, sensitive or low level measurements. There's a bunch of different parameters you can also define when you're making a sweep measurement with an SMU. Showing some of the key ones here. Typically, you can do either what's called a linear sweep, where the points are, as the name implies, equally spaced and linearly, or you can also do a logarithmic sweep, where they're spaced equally in a logarithmic sense. And we can do both single and double sweeps on our SMUs. And again, there's different reasons you might want to do both of these. Also want to mention that you might sometimes see this term var1, and especially in our older instruments, that just means variable 1, and it means the sweep variable. It's just the terminology for the older products. The newer products just say sweep. Another type of sweep measurement that's very common is to do what I call a subordinate sweep. As you can see here, you have the primary sweep variable and a secondary sweep variable, or subordinate variable, which is sometimes called var2. And that just means that for every value you specify for var2, the primary variable, sweep variable, will repeat. And again, why would you want to do that? Well, it's actually very useful if you wanted to make, say, a family of curves, like an IDVD measurement where you want to have different IDVD curves, but you want to vary the gate voltage. So there, the gate voltage is obviously the var2 value, and the ID values, are used for the primary sweep. You also sometimes might want to do a synchronous sweep where you have something synchronized with another variable. But again, that's kind of an older a feature, older parameter you'll see on the older instruments. It's not really so necessary on the newer products because there's other ways of doing the same thing. But I wanted to show it just for completeness sake. So it's very important to actually understand the timing parameters for a sweep measurement because that in the end can determine how good your data is. And you need to understand that you can set both a hold time, hold time is the initial time before the sweep actually starts. And then the delay time is the time right at the instrument waits after you change the value to the next value in the sweep before it actually starts making the measurement. Now, why do I want to do that? Well, if I have maybe a lot of capacitance or other factors affecting my measurement, what it basically does is allows the values or voltages, currents to stabilize before I try to make the measurement. And that can be very important in different situations. So again, if you're trying to make a sweep measurement and you're getting strange data, you might try playing with these parameters to see if, in fact, that's what's causing the problem with your measurement. So again, it's very important to understand these parameters and use them properly if you're getting unstable measurements. In parametric tests, just want to point out 4 is kind of a magic number because we generally recommend that you have at least 4 SMUs if you're going to do general purpose characterization. And why is that? Well, it's because actually transistors, as shown here, for example, a MOSFET, are generally 4 terminal devices. People sometimes forget that there's not just a drain, gate, source, but there's also the substrate connection. And on a lot of times, and that's very important because the voltage on the substrate will affect the values of the, I should say, the results you get from the other types of measurements. So again, that's very important. It's also very important to have the SMUs all synchronized with each other for obvious reasons. You want to have the measurements, working together, and everything has to be timed correctly. So again, this is very important in parametric tests, 4 SMUs that are completely synchronized with each other. In this next section, I'm going to cover some tips for making accurate low-level measurements. When you're making low-level measurements, your main concern is going to be probably noise. So there's different ways you can reduce noise. 2 of them are shown here on the slide. So on the left, you can see shielding. Basically, you're creating essentially a Faraday cage around your equipment by using a grounded shield to surround it completely, and that will help eliminate a lot of the noise. As I mentioned earlier when I talked about integration time, of course, you can also do averaging, which is basically averaging over 1 or more power line cycles, which again can help to eliminate noise as well. One source of noise sometimes that people aren't so aware of is actually the noise generated by their cables. And this is really more what I would call electromechanical noise in the sense that it's electrical noise generated when the cable is compressed or bent. So again, there's 2 different effects. They're kind of similar. One's the triboelectric effect, and there's also the piezoelectric effect. But again, they have the same net effect on your equipment, which is, again, they're going to create noise. So you want to make sure the cables are hopefully fixed down and not moving, and you don't have any mechanical stress. They're not clamped down so hard that you're stressing them. I do want to mention that actually our cables, as shown on the right, we actually have a semiconductor layer between the insulation and inner shield, and that really helps to reduce the noise. It's actually really hard to see on this graph, but the red line that's jumping all over the place is a standard cable. Ours is a blue line, which is actually very straight. It's actually right on there. It's really hard to see, but there's actually a big difference in terms of the noise generated by our cables and a lot of our competitors' cables. So again, just mentioning that quality of the cable you use also does have a big impact on the noise that you're going to see in a measurement. Cable capacitance also has an effect on your measurements. Especially if you're trying to do like a sweep measurement, you want to change the value of whatever you're measuring. As I mentioned, there's parameters. There's like a hold time, which is the initial time before you start the measurement, and also the wait time. the time between you wait after the voltage changes before starting a measurement. So these are very important parameters. So again, if you have a lot of capacitance in your setup and you're trying to do maybe a sweep measurement, you're not getting good results, try playing around with the hold time and the wait time and see if that will actually improve your measurement results. Now, especially if you're making measurements on a wafer, although this also does hold true for package devices, but more prominent on wafers, you'll find that the probes and some of the other cables and things will actually just have some stray leakage currents associated with them that make it very hard to make a low-level current measurement. But fortunately, if those currents are consistent, we actually have a way to subtract those out automatically so that you can reduce those and get more consistent and better measurements. On virtually all of our parameter analyzers, there's something called the SMU0 function. And what that does is it actually allows you to remove the stray leakage currents automatically. So if you turn that on, you do that actually, first, of course, with the probe tips up, not touching your devices. You turn that on, it will measure all the stray leakage currents going through the probes and cables and everything. And then it records them, it shows them in the table as shown on this slide. And then what happens when you touch the thing back down on your prober, it will actually subtract those out. So you get very consistent, clean measurements, only measuring what's actually happening on your DUT and not measuring those stray currents. And this just shows an example graph measuring current versus time. This is actually an SMU measurement open, so there's nothing touching the SMU output. We've ran the zero offset cancellation on it, however, and you can see using just short integration, which means I'm actually integrating less than a power line cycle, so very short integration, very little averaging actually happening, but notice that I can maintain a very low level, plus or minus about 3 femtoamp baseline, which is typically what you would expect to see on a precision or high resolution SMUs, again, if it's open circuit. So this is one way you can also, by the way, verify if your SMUs are working correctly or not. Remember earlier when I talked about triaxial cables and I explained that there's a driven guard, so you have the center conductor and then there's a driven guard and then you have the outer ground shield. You can actually also do the same thing with a wafer chuck, believe it or not. And so there are manufacturers that have guarded chucks as shown in this diagram. And again, the effect of doing this on a wafer is similar to what the benefits you get from doing it on a cable, is that it's obviously going to eliminate a lot of the stray leakage currents that you would otherwise see. So again, you can actually make low-level currents much easier and much more reliably if you have a guarded chuck on your wafer prober. So I'm kind of finishing up my discussion of source measure units here. I just want to point out there's kind of 3 basic classifications you could kind of give them. I've really been talking mostly about precision SMUs so far. Again, they're designed for the characterization of semiconductor devices, and as I said, they're 4-quadrant. They have very low-level measurement capabilities, source sync current, things like that. There's also SMUs that are made more for power devices, as shown in the middle column, where they have very high voltage, high current, thousands of volts, hundreds of amps of current potentially, but still can measure pretty low values. There's also SMUs that are made, and I haven't really talked about this, but there's what they call fast transient response SMUs. And those are really kind of a different area, but they're more for like battery testing, things like that. Typically, they only have 2-quadrant operation because they don't need to go negative voltage. But again, they're more for testing things like battery drain or maybe RF amps, RF amplifiers, things like that. So again, these are the 3 basic kind of main categories of SMUs you'll find. And I just want to point out before I move on that we actually have SMUs that fit in all these categories. So again, for precision area, we have our modular PXI-based SMUs. We also have the benchtop, the B2100B and BL series, as well as our pretty well-established analyzers, the E5270B and the B1500A. For power device testing, we've got both the B1505 power device analyzer, curve tracer, as the B1506, which is a power device analyzer, more focused on people that are just doing circuit design. And again, for the fast transient response, people want to do battery drain analysis and other things like that, where they need to measure things over time. We've got the N6700 series, which includes the N6700C and the N6705C. So the key points of this section, or key points of what I've talked about so far, are really these 4 points shown here. Again, as I said, SMUs used for parametric test really do have special needs. They have to have special capabilities, ultra low resolution, 4-quadrant operation, triaxial outputs, 4-wire or Kelvin measurement capability, auto ranging, things like that. Also pointing out that to really want to make the good low quality measurements, you have to have also other parts, not just the instrumentation, but you need to have good cables, good test fixturing, a quality wafer prober if that's what you're doing, things like that. Also, again, reminding you that there's really 4 SMUs is kind of the magic number for parametric tests because MOSFETs are 4-terminal devices. You want to have those synchronized and able to operate together in unison. Just a general point, I think it's pretty obvious, but when you're actually selecting equipment for the parametric test, you really should keep in mind not just your current needs, but also what needs you might have in the future and how expandable your solution that you're purchasing today is if your needs do change in the future. In this section, I'm going to give you a brief overview of capacitance in semiconductor devices. What is capacitance? Well, if I have 2 adjacent electrodes, capacitance is the ratio of the magnitude of the charge stored on either one of those electrodes divided by the voltage difference between them. Again, remember, it's just the charge on one or the other because in a capacitor, the net charge is going to be 0 because of charge balance, right? And again, probably when you're looking at capacitance, the most important equation is shown on the bottom right of this slide, Q equals CV. I'll get back to that later, why that's important, but obviously we use that a lot when we're actually trying to calculate capacitance in semiconductor devices. So why is semiconductor device capacitance important? And I'll show you later why more about this as well, but there's lots of different parameters that actually can only calculate out from measuring capacitance that are not really possible to calculate out from current voltage measurements. But again, some of the common ones you can see here. And by the way, normally in semiconductor devices, we're measuring either MOSFETs or other types of transistors, or maybe some interlayer connections as well. But again, there's on the left, you can see a sort of generic MOSFET showing the different capacitances that are there. But again, from calculating out or measuring the capacitance, you can determine real basic things, obviously, like the dielectric thickness, but also a lot more complicated parameters as well, as I'll show you in a little bit. So what are the types of capacitance measurement we can do in semiconductor devices? So, and by the way, semiconductor devices are not the same as discrete capacitors because semiconductor devices, typically the capacitance will vary with some of their parameter. Most of the time we look at capacitance versus voltage. In other words, we look at a fixed DC voltage or apply a fixed DC voltage to a semiconductor device and measure the capacitance. You can also measure though capacitance versus signal frequency or even time, depending on certain situations. But I would say the vast majority of the time in parametric tests, we're making capacitance versus voltage measurements, CV measurements. So in this example on the upper right, I'm basically measuring the gate capacitance, C sub G, versus applied gate voltage. So again, this is a DC voltage I'm applying, plotted on the x-axis, but I'm also at the same time, to make this measurement, I'll show you later, I'm applying an AC signal that's actually in the millivolt range to measure. But the important point to note here is the actual capacitance does vary with applied voltage. In other words, it starts off at a max value, as you can see, then it will typically decrease and then snap back up. If I'm doing a quasi-static measurement or if I'm doing a high frequency measurement, it'll generally flatten out. I'll talk about that a little bit more in a couple of slides to explain what those mean. But the important point on this slide simply is to note that there's a lot of important parameters that can only be extracted by measuring capacitance in this way. And again, things like density of acceptors, depletion layer depth, things like that. And again, that's why we actually make capacitance measurements on semiconductor devices. In this next section, I'm going to be talking about the basic ways that we measure capacitance on semiconductor devices. Again, there's 2 basic ways we do it. One is with a LCR meter, or also we also do what's called a quasi-static CV measurement. And I'll talk about the techniques to do both. So I'll be honest when I start here and say that capacitance measurements can actually be kind of frustrating at times. They are much more difficult than IV measurements for a variety of reasons. And just the 3 bullet points I show here are some of the probably the most highest level of pain points that you have. One of these, of course, is that when you make the IV measurements with the SMUs, as I mentioned, you're using triaxial cables. But when you actually make a CV measurement using an LCR meter, that's B and C cables. So you have to have some way to switch between those two easily. You also, when you do a capacitance measurement, you have to do a lot more calibration. You have to do, at a minimum, open short. I'll talk about that later. Open short, and also load calibration. So that's, having an easy way to do that is important. And also, as I'll mention later, I'll talk about quasi-static and high frequency. You really need a solution that can do both easily, and because you actually need to do both types of CV measurement to get complete data on a semiconductor device. As I just mentioned, you actually need to do both quasi-static CV and high-frequency CV measurements on a semiconductor device to really get a complete understanding of how it's operating and all its different parameters. So people do both of these, and at the bottom here, I've got a little table that kind of shows some basic information. Again, there's different ways of doing quasi-static. You can do a ramp or a step voltage method. It's a charge measurement method, typically now done with SMUs. And again, since it's using SMUs, it uses triaxial connections. The high frequency CV measurement, again, typically we usually do that around megahertz, uses an LCR meter with an auto balancing bridge, and it uses B and C connectors. And so there's some things you have to keep in mind as you're doing those high frequency measurements in terms of compensation and things like that as well. So I'll cover in the following slides some of the more details about both of these techniques. I'm going to start off first talking about quasi-static CV measurements. So this slide kind of tries to explain the difference between a quasi-static and a high-frequency measurement. So I think maybe the easiest way to think about this is the fact that the ionized acceptors shown on the lower right diagram there, they're basically, come from generation recombination effects, which are relatively slow. So if you try to change the voltage quickly, in order for the charge balance to maintain, basically those have to, those ionized acceptors have to react. And what happens is you get the summation of the COX and the CD together. And in series, that's going to actually reduce the total value of the measured capacitance. Now, if you go slowly enough so that the ionized acceptors are not involved in this, then basically you only see the COX portion of this equation and you get the quasi-static response. So again, you have to have both quasi-static and high frequency responses if you want to measure certain things like interface trap charge. So, but basically this is kind of the difference between a quasi-static and a high frequency measurement. So some of you might be wondering, I said we make quasi-static measurements with a SMU. How do we do that? Well, we do it in a similar way that almost the way we would do a sweep measurement on the SMU, except as you can see, what we actually do is when we're making a quasi-static measurement, we're sweeping the voltage, but at each point in the voltage as we sweep, we actually do an additional little voltage bump. I call it a bump. And that bump actually creates that delta V, creates a change in the charge stored in the capacitor, a delta Q. Now you can measure that charge by monitoring the current going into the device. And if you know the time, of course, you can average it out and calculate out the delta Q. And then using the basic equation I talked about earlier, C equals Q over V, we can actually calculate capacitance at each point along the curve as we sweep. What are the needs of the equipment you need to have to make an accurate QSCV measurement with SMUs? Well, as I mentioned, of course, you need to have very good low current measurement because, again, you're integrating the current over time, and also, by the way, good time measurement capabilities as well to get an accurate delta Q for the measurement. You also have to have, obviously, a good accurate voltage sweep capability for the delta V. You also have to, again, have a built-in algorithm in the instrument for doing the quasi-static calculation. And we actually do have all of these capabilities in the B1500A. We can do quasi-static CV with the SMUs very easily. And shown in the upper right there is a graph. Actually, I took a number of years ago on a device, but basically it shows quasi-static CV made with the SMUs, and then a high-frequency CV made with the built-in capacitance measurement unit as well. And I'll talk about that in a little bit. So I just covered quasi-static CV measurement. Now in this next section, I'm going to spend some time talking about high-frequency capacitance measurement using what's commonly known as an LCR meter. So this diagram on this slide shows the operation of a capacitance, or really generic LCR meter. Notice that the high current, high potential terminals feed into the DUT, but the actual measurement is made at the low terminals, the LC and LP terminals. So that's kind of important thing to remember, and I'll show why later. Also note that essentially the circuit looks, or at least the simplified circuit, and it's pretty true, it's kind of similar to an op-amp circuit with feedback. So the terminals on the other side of the DUT actually are a virtual ground. And again, what we actually do when we're making the capacitance measurement is we're putting a sine wave into our device, again, at typically very low levels, like millivolt levels, and then we get a sine wave out, and we're measuring that on the other side. And because of that, we're actually getting two pieces of information, all right? So we have the magnitude change and the phase change. And because of that, we can actually get to calculate out two pieces of data. So if you look at any LCR meter, they always will give you, of course, magnitude and phase, but there's like a little functionality built into it that it will also tell you a resistance and capacitance, or inductance and resistance, or whatever, in series, parallel, different combinations. And what you're really doing is you're telling the instrument, that's what I'm measuring. And if that's what I'm measuring, the instrument says, oh, based on the magnitude and phase change I see, well, this is the values that would correspond to that in a circuit. So it's an important kind of point to keep in mind that that's really how the capacitance meter is actually working. One major difference between making capacitance measurement and making IB measurements is that you have to worry about things like cable length and cable compensation. I mean, of course, in IB measurements, we as I mentioned, we have some concerns about the cabling because it can add some capacitance and delay, and there's some other factors. But in general, it's not as big an issue. But with a capacitance meter, especially an LCR meter, we have to worry about the cable. So we connect the cable to the outputs of the meter, and then that cable goes over to our DUT at some point. Maybe there's some additional fixturing. Well, guess what? We actually have to do some compensation on that cable to correct for the inherent capacitance, inductance, and resistance of that cable. And that's otherwise we're going to get improper measurement data when we try to make our measurements. So this slide shows the issues with shielding and two-terminal connections. So again, on the left there is just a basic two-terminal connection, whereas you can see that that was something you really should never do because of the noise that's going to be created if you actually tried to make a measurement. Again, there's magnetic flux generated, and you're basically going to get a lot of noise, and it's going to be a very bad measurement. The three-terminal connection shown in the center only connects the outer shield surrounding the extension cables on one side, and that's better, but it's still going to give you problems because there's not a complete return path for the any currents that are generated in those outer shields. Whereas the shielded two-terminal connection on the right, see there's those green arrows there show a kind of a current return path. So there's a complete path. So there's going to be an induced current created in those shields from the current that's actually flowing into the DUT. And by connecting them together on both sides, you give a path for that to complete, and it's going to basically give you better, as a result, you're going to get better measurement results. The other thing you need to do with the cables, besides, of course, using the proper type of connections for the cables, is at a bare minimum on a capacitance measurement, you really need to do open short compensation. And all capacitance meters basically have this capability built in, as well as the ones that are, we have for our B1500 series. And it just means simply that you're going to have the cables going out to your DUT. You're going to do the open. You just make sure that there's no DUT connected there, and you, lift it up or just disconnect the cables, and you run the open compensation routine, and it'll do the open compensation. And then you short those two cables together with a wire or some other means, and you run the short compensation, and that will actually eliminate a lot of the residual impedance and capacitance effects on the cables. So that'll give you pretty good results in general. A lot of times that's all you need to do. Now, depending on the frequencies you want to measure at, you may also need to do a load compensation. Typically, if you're only going up to about a megahertz in frequency with your capacitance meter, and again, remember the megahertz means that's the sine wave that you're putting into the DUT, and again, you're putting that sine wave in, measuring magnitude and phase change. But the frequency of that little sine wave you're putting into your DUT, if it goes above a megahertz, then you actually can get some additional error unless you do what's called a load compensation. So the load is actually a little trickier because you really need to have a calibrated load standard, maybe like a 50 ohm or something load. And so again, what you do, the load compensation, you touch down with the probes, you put the touch down to your load, your calibrated load, and you run the load compensation. And then that actually gives you even better accuracy, again, especially as you go to higher frequencies, typically above about a megahertz. So this slide shows a couple different things. Again, on the left there, you can see measurement error done on some different devices with actually no compensation at all. So again, you can see that you do get quite a bit of measurement error right away if you don't have any compensation. So as I said, you have to do at least minimum open short compensation. Now the graph on the right does a comparison, versus frequency for a device, the measurement error you get basically with just open short compensation versus doing the open short load compensation. So again, as you can see from this data, if you don't go above a megahertz, you're probably okay. You don't need to worry about doing the load compensation. But if you're going to go to higher measurement frequencies with your C meter, you probably should consider doing some sort of load compensation. Otherwise, you are going to get just increased measurement error as you go to higher and higher frequencies. If you're going to make measurements on a wafer with a capacitance meter, it's very important that you understand that wafer chuck you've got there has a profound effect on the measurements you make. It becomes part of the measurement setup. And I think people don't always think about this when they're making measurements on a wafer prober, but it's an important point to keep in mind. The biggest thing you have to do is to, as shown on this diagram here, you always want to make sure that you connect the low side of your capacitance meter to the actual DUT you're measuring, the wafer, and the high side to the chuck. And I'll explain why that is on the next slide. So the reason you want to always connect the low side to your DUT is because, again, that wafer chuck is actually, in reality, a large capacitor. And what is a capacitor to an AC signal? It's a short. So again, we're applying a sine wave to measure capacitance, right? So the chuck creates an AC short to ground. So looking on the left there, what if I have the high side connected to the DUT and the low side connected to the chuck? Well, I inject current into my DUT, and notice that because there is that leakage path to ground through the chuck, not all the current that goes through my DUT actually gets measured. Now remember, the measurement happens on the low side. That's important to remember. The low side of the meter makes the measurement. So because the current splits, as shown on the left, it's gonna basically not give you accurate data. Now on the right, if I connect the low side to my DUT, well, okay, I inject the HPHC terminals are still, of course, pushing current through the DUT, and some of it is going to go to the leakage path to ground, but it doesn't matter because I'm measuring at the low side, and everything that goes through the DUT is now being measured at the low side of the terminal. So there's no split where I'm actually making the measurement. And that's why basically doing this simple change of how you make the measurement will actually make a big difference in the measurement results you get. There's actually a second reason that you also shouldn't connect the high side to the DUT when you're making measurements. And that's because not only is that wafer chuck a giant capacitor, it's actually also a pretty good antenna. And it can actually pick up a lot of stray electromagnetic noise. So if you connect it up as shown here with the high side to the DUT, it actually can inject that noise right into your low side, into the ammeter, and you're going to actually get bad results as well. So this is actually just another reason why you don't want to connect the high side to your DUT. You actually always want to connect the low side of the C meter to your DUT when you're making capacitance measurements. And to prove my point, here's some measurement data taken using a capacitance meter, LCR meter. And on the left there, you can see what happens if we connect the high side of the C meter to the gate. You can see that there's a tremendous amount of noise created on the measurement, so it looks very, very ugly. It's not very clean. Whereas on the right side, you can see that when I connect the high side to the bulk and the low side to my actual DUT, I get very, very clean measurements across a wide variety of frequencies. So again, this measurement data just confirms what I told you in the sense that you always want to connect the low side of your C meter to your DUT. So I told you or explained a little bit about capacitance measurement on semiconductor devices. I talked about the quasi-static capacitance measurement, why it's important, the high frequency measurement using the LCR meter, why that's important, and some of the tricks there. So basically now I'm going to talk about how do we put all that together into a complete system to be able to make consistent and accurate capacitance measurements as well as IV measurements, because we also still obviously need to make current voltage measurements as well. So as an example of a solution to this, I'll talk about the B1500 device analyzer. Of course, it can actually make both quasi-static CV and high-frequency CV measurements, and it can also obviously make IV measurements. And it's got lots of what we call application tests available to help you do this, and it's very cost-effective, configurable. We have something in it available for it, a module called the multi-frequency capacitance measurement module or unit, MFCMU. It can do CV, CT, CF measurements, and it can measure from 1 kilohertz to 5 megahertz. Of course, we also have SMUs that are very accurate. We can actually go down to 0.1 femtoamp, and the SMUs also all support making quasi-static CV measurements with the measurement I showed earlier. And then finally, we have another accessory called the SMU-CMU Unify unit, which actually allows you to multiplex or switch between the SMU and the capacitance measurement unit very easily and very efficiently. So actually in the past, many years ago, people sometimes would actually buy a switching matrix with maybe just one card in it and use it with their parameter analyzer, simply because the switching matrix allowed them to multiplex between the capacitance meter, which has, again, B and C outputs, and the SMUs, which have triaxial. But we came out with this thing called the SCAU, a few years ago, and it works with the B1500. Now it's shown in the upper right there, and it basically is shown in the diagram. It allows you to switch between two SMUs and the capacitance measurement unit on the instrument, and it's pretty much seamlessly, and it's controlled by the software, so it automatically switches in the right resources to make whatever measurement you want to make automatically. It also has this optional accessory we highly recommend. Typically, it's called the guard switch unit. You can see it in the bottom right there. What it basically does is it shorts out the guards together when you're making a capacitance measurement and leaves them open when you're making an IV measurement. What that does, I'm not going to go into all the details, but if you do that, it will actually give you better capacitance measurement results than if you don't do that. And it's important, of course, you don't want them shorted together when you're making an IV measurement because they're going to be at different voltages. But it does this for you automatically, and again, it's something where you don't have to think about it. One other quick comment before I leave. So that picture in the upper right there showing the SCAU connected directly to the output of the instrument is not the way you'd really want to use it in practice. We actually have an extension cable that can go a couple of meters at least beyond that. And so what we normally do is you connect this extension cable to the instrument, and then the extension cable connects to the SCAU, and you mount the SCAU on your wafer prober or whatever you're probing because you really want to keep the meter will compensate exactly or automatically for that extension cable. And that means that the only thing you actually have to do compensation, like open short calibration on, is whatever additional cables you've added beyond the SCUU. And I'll show you a picture on a wafer prober later how that actually works. So the benefit of having the guard switch unit is that by shorting those guards together when you're actually making a capacitance measurement, it actually stabilizes the kind of residual inductance, especially if the cable gets moved around. So it will give you better results. And again, shown here on this slide is just some data that, especially as you go to larger values of capacitance and higher frequencies, if you don't use the guard switch unit, you will get additional error in your measurement. In some cases, it can get kind of extreme, but again, it's a nice accessory. We normally recommend people use it. It doesn't, again, cost very much, but it's a good accessory to have and use when you're actually, if you want to get the most accurate possible capacitance measurements when you're making a CV measurement. This slide kind of summarizes what I talked about. It shows the actual proper connections you should have if you're using our SMU-CMU Unify Unit, SCUU, with the wafer prober. So again, you can see that there's this 3-meter cable shown that it runs off and it actually goes to the instrument. And that cable is compensated for automatically, so you don't have to worry about compensation on that. The SCUU, then you want to mount on the wafer prober, and we actually have a magnetic stand that you can get. It's shown in the picture as well. And that's really nice because otherwise it prevents the cable from flopping over. Makes a nice stable thing. And then you want to, again, as I said, you want to keep the cables going off of that SCUU as short as possible, because those are the cables you actually have to compensate for with your open short or potentially load calibration. But this arrangement allows you to keep those cables short. And again, also you can see that you can mount the guard switch unit if you want to use that as well, which we do recommend. You can mount that on there as well and feed that into your wafer prober so that those are shorted. And again, this creates a nice, complete, very easy to use solution for making CV and IV measurements on wafer. Hopefully I've convinced you that capacitance measurement is essential for parametric device characterization, and also that you need to do both the quasi-static CV and the high frequency CV if you want to get a full characterization of your MOSFET device. Now, if you want to make QSCV measurements, you actually, again, have to have instrumentation with capability to make very accurate low current measurements over precise time increments, as I talked about earlier. For the HFCV portion, you need some sort of LCR or capacitance meter that has support for cabling and error compensation to, of course, eliminate residual impedance and stray capacitance effects. Also want to emphasize, again, as a reminder, that if you're making on-wafer measurements, especially capacitance measurements, you need to carefully consider the effect of the wafer chuck on the actual measurement results. Again, remember, it becomes part of the measurement setup, so you got to take it into account. And again, finally, a semiconductor parameter analyzer that has both quasi-static CV and high-frequency CV capability and the ability to switch between these two types of measurements is generally the best solution for this type of application. Okay, we covered a lot of material in the last hour or so, I think everybody needs to take a 10 or so minute break. So let's take a break and come back in maybe 10 or 15 minutes, and I'll finish up with the discussion of testing memory cells and also high-speed testing.
We have now the 15 minutes break. We will be back after the 15 minutes break, and there will be a form for both people that are listening over Zoom and over YouTube. If you fill that form, you will receive further information from Keysight. And remember that at the end of the second part of the presentation, the presenter, Alan, and also Alan Wadsworth and also Teja Kohatmasu, they will be available to answer your questions. So please remember, there will be a form for you to fill out and receive further information. And at the end of the second part, that will start in about 15 minutes, the presenter will be available to answer your questions. Thank you. Thank you.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes, but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So, get a taste of our work. Appreciate the little things, and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.
You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Tools and outfits. They're practical, give us comfort, create unity. They're part of an identity. At IMEC, we've got tools and outfits too. They help us do our jobs. But underneath them, there's us. And we perform science. Mathematical and accurate data, together with powerful gray matter that thinks out of the box, is the foundation for our creations. And the accumulation of digitization for the continuation of our population is our destination. Need a translation? Here's a simplification. At IMEC, we create possibilities. Possibilities that shape our future. One with healthier people, safer transportation, streamlined logistics and manufacturing, smarter cities, smarter education, and cleaner energy. We use brains and science to advance microchips and software. We combine them to create a meaningful change in our society. Over 5,000 unique people from over 95 nationalities and an extensive network of partnerships give us the capability to revolutionize the world, and maybe even more. IMEC, embracing a better life.
Somewhere, maybe right at this very moment, The next technology breakthrough is about to inspire the next generation of minds, thanks in part to Keysight Technologies. As a future technologies enabler, Keysight goes where the electronic signal goes, helping to unlock measurement insights at leading technology companies, so they can go from an idea to the marketplace faster and at a lower cost. And business is good, because technology is changing at an exponential pace, with more demands for more devices, faster, smaller, longer lasting, anywhere, anytime, smarter, connected. It's inspiring today's megatrends, the ideas that the world's brightest minds are already working on. By quietly partnering with the biggest names in the global technology business, we're helping to realize these future innovations. They're top engineers working side by side with our top engineers to overcome ever-increasing electronic design, development, and production challenges. How do we do it? Measurement, because you can only improve what you can measure. And Keysight has the electronic design, test, and services solutions that lead the industry, helping our customers get to market faster. Let's go back to that classroom. Imagine the potential of using real-time technology to teach and learn, empowering discussion and ideas across the globe, to and from anyone, anywhere. Now let's say that idea requires a wireless device that's 10 times more capable than current technology. That's where we get involved. Before that idea can begin to take shape, Keysight is helping make sure it will succeed, thanks in part to our participation alongside governments and industry leaders in the groups that help create the standards for technologies of tomorrow. We're involved early, which means Keysight can anticipate what will need to change and begin development of design and test solutions while helping to define the new standards. As a result, our customers have an early advantage because we'll supply the expertise they need right when they need it. In the world of R&D, long gone are the days of going straight to physical prototype. Today, it's all about software simulation. It saves expensive hardware prototyping cycles, development costs, time, and no other company is more respected for software solutions than Keysight. In fact, our ESOF electronic design automation software simulates the precise electronic behavior of the components in a customer's virtual prototype. It's the standard used by over 2/3 of the world's high-frequency electronic designers, empowering customers to confidently bulletproof designs long before they're built. As the physical prototype is made, customers turn to Keysight once again to validate that it works properly in the lab and in a variety of real-world environments. These complex tests help prevent losses that technology companies may face if there is an undetected defect hidden in their product. The device is finally ready for mass production, and Keysight is ready to help its customers get the latest, greatest technology into the hands of eager buyers. Tens of millions of units are at stake here. Customers rely on Keysight to keep the line moving with accurate test solutions and tools to help them maintain quality. The result? A bug-free, cost-effective, high-quality product in the hands of people who need it. Faster. If there's a signal to be measured, Keysight is there, from satellites to base stations to mobile devices. Our job is to ensure the signal is clear, true, and reliable. It's what we do for communications and beyond, energy, aerospace and defense, computers and semiconductors, automotive electronics and safety, industrial applications, education and research. In fact, the minds of Keysight have been behind the most important technology breakthroughs of the last century. And today we offer world-class services along with the broadest design and test portfolio of any company in the world. With our global network of experts, we provide an emerging array of services to accelerate our customers' business goals, including calibrating multi-vendor test instruments, managing asset portfolios, and providing training, consulting, and other professional services. As a premier future technologies enabler, partnering with customers to help them move from design through manufacturing faster and more efficiently, no other electronic design and test company is better poised to help deliver what's next. First.
ABSEMI, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. ABCMI promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country, producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets, fourth in mobile phones, seventh in the computer market, and ninth in the production and sale of vehicles. Moreover, it is expected that Brazil will be prominently ranked in terms of connectivity in the coming years, from the interconnection of productive processes, either of the agribusiness or of the modern automotive industry, to the so-called Internet of Things devices. Due to public policies implemented in the last decade, together with the relevant invests made in the country by domestic and foreign industries, Brazil increases its relevancy in the global semiconductor chain each year. The industry
So now we have the second part that will start with flash memory testing, and after that BTI and RTN will be addressed among other topics. And please don't forget to fill the form. We already have the link on the chat to get further information, further support from Keysight. So now we can start. The second part will be about 45 minutes. After that, we will have the live question and answers. Okay, thank you very much.
In this next section, I'm going to talk about flash memory cell testing. But before I go on, let me just point out that the things I'm talking about for testing flash memory cells, of course, are equally applicable to testing other types of non-volatile memory cells like resistive memory, phase change memory, or things like that. So not specific necessarily to just flash memory cells. This slide shows sort of just the very basics of flash cell memory, how it works. So again, a flash memory cell is really just a FET or field effect transistor with an extra floating gate. And then by injecting charge or removing charge from the floating gate, basically what we're doing is we're influencing the threshold voltage of the FET. And by doing that, we can essentially program it to be either a 0 or a 1. In other words, it's changing the status of a memory. So you can kind of see there in the middle of this graph, there's a different. Obviously, I can see there's a clear delta threshold difference between a programmed and a non-programmed transistor. So to actually do this right erase, you actually have to use some sort of a pulse generator unit, some sort of pulsing thing to do the right erase of the cell. But we actually go ahead and we use SMUs to, of course, measure the threshold voltage of the cell after it's been programmed or deprogrammed or written to and erased, I suppose I should say. There's a couple of different ways that you can program a flash memory cell. This one shows something called Fowler-Nordheim tunneling current, FN. And Fowler-Nordheim tunneling is tunneling that occurs through, as you can see in that middle diagram there, when you have really extreme band bending in the semiconductor device, then there's an area of the band that's very thin, I suppose I should say, if that's the right terminology. But it's much easier for electrons to tunnel through that part of the band than it, of course, is the thicker part. So that's basically how Fowler-Nordheim tunneling works. Again, it's distinctive from traditional or standard electron tunneling. But again, this is the one way that you can get charge into onto or off of the floating gate of a flash memory FET. The second method you can use to deprogram a flash memory FET is to use just hot electrons. Okay, and again, hot electrons are just electrons with enough energy to overcome the band gap in the semiconductor and jump up into that floating gate. So again, these are just the two methods. It may or may not be relevant to how you actually test the devices, but I just wanted to make sure that it's clear there are two different generally types of techniques for doing the flash memory testing. Although there are actually a number of different factors you can look at when characterizing flash memory cells, the main reliability concern really is write erase endurance testing. And as I mentioned, of course, before, by adding or removing charge from the floating gate, we basically shift the threshold of the transistor, and that determines whether we're at a 0 or 1. However, as you do these write erases, you actually cause a very slight amount of damage to the oxide film each time. Now, over time, this accumulated damage will actually work to decrease the voltage difference between the 0 and 1 states, as shown here in the lower part of this slide. So again, if these get too close together, eventually that's going to be effectively a failure because you can't distinguish between a written or erased cell anymore. So again, understanding how many cycles this takes is very important for flash cell, memory cell reliability. So the problem with a lot of conventional solutions for flash memory cell testing is they just don't have the capabilities to actually test the memory cells efficiently. That's because really an output voltage of plus or minus 40 volts is pretty necessary. Also having the ability to tri-state the outputs is very important. Another thing is you really need to have a pulse generator that has very good voltage accuracy on the pulses if you want to get accurate lifetime predictions on the cells. Again, you also need to have some way of doing 3-level and also open state pulsing capability in order to get the testing faster. And again, just in general, some pulse generators don't have the ability to generate any kind of complex waveforms if there's some more exotic NVM structure, or it could also be testing maybe something else like a resistive memory or phase change memory, which could require a more complicated pulsing arrangement. So here I'm showing you our solution for flash memory cell test. So we have a specialized module, the high voltage semiconductor pulse generator unit, or HV-SPGU module. And it's basically designed for this type of thing. It actually has 2 channels per module. You can actually put up to 5 modules or 10 channels in an instrument. The important thing is it actually has a plus or minus 40 volt pulse supply capability. It's got very good voltage control and its pulsing. Also, it can do 3-level pulses as well as open state pulses on each channel. It also can generate complex waveforms, has a linear arbitrary waveform generation capability, and it's fully integrated, of course, into the software for the B1500A. So we can do very long write erase endurance testing without any issues, and we can do it very fast and very efficiently for both NAND cells as well as NOR cells. Now, we also have some accessories I'm not going to show here. I don't want to get into too many details on this, but if you need to open the output state many times, obviously you want to not use a mechanical relay, you want to use a semiconductor relay. So we have some accessories that you can get for the B1500A that will work with it automatically, fully integrated into the software. So if you want to do write erase testing where you have to have some of the paths open repeatedly, we actually can do that very easily. And again, this gives you massive improvements in the throughput test time, as I'll show you in a second. So using this solution, this slide shows you some of the improvements we've achieved in throughput versus some of the older solutions. Now, the 4155 and 56 were pretty old instruments. I mean, they date back to the 1990s. and they've been discontinued or obsolete for some time now. But we did have a solution using those older instruments, but the pulse generator we had for those was really not as good as the newer one we have. So you can see that to do a right erase cycle test of 1,000,000 could take actually days to do it. With the newer solution, again, depending on how many, what type of flash memory you're testing, and also how many SPGU channels you have, we can actually reduce that test time dramatically to just a matter of less than a day or less, or even just a few hours, as you can see from this table. So again, if you need to test flash or do flash memory cell endurance testing, this is really a very nice and efficient solution for doing that. In this section, I'm going to be talking about fast pulse measurement techniques and tools, which is actually a very interesting area of parametric tests, because really my personal feeling is a lot of the future stuff that people are doing is all based on fast pulse measurements. So again, this is kind of the future area that parametric test is heading towards. So just a review real quick here. What is a pulse? What do I mean by a pulsed IV measurement? Again, in a pulsed IV measurement, we're using pulses, not DC signal levels, obviously. The important point is that pulses can actually vary quite a bit. You can have pulses that are milliseconds, or you can also have pulses that are down to nanoseconds. Now, nanoseconds is where you're really talking about ultra fast measurements. But again, this table just shows the kind of difference between a spot measurement made as a DC and a pulse, and also a sweep measurement made DC or pulsed measurement. And again, SMUs can do milliseconds, but if you need to go faster than that, you really need to be thinking about some other type of measurement solution to get down to that like nanosecond level of pulsing. When you go from making DC measurements or even pulse measurements with an SMU to making what I would call fast transient IV measurements, there typically are some trade-offs you have to think about. If you look at that graph in the upper right there, it kind of shows the difference between trying to make maybe a fast pulse measurement and an SMU or long averaging type measurement. And again, when you're making SMU measurements, we generally assume that we can have as long a wait time as we want, or hold time to stabilize everything out before we make the measurement. We oftentimes don't have that luxury in a fast pulse measurement, because again, we're trying to pulse very quickly, so sometimes our equipment doesn't stabilize all that fast. So you may have to make some trade-offs. Obviously, if you're making a fast pulse measurement, you may have to make some trade-offs between speed and accuracy. And you're probably not going to be able to get as many bits of resolution when you're making a fast pulse measurement as when you're making, say, a long-term type measurement on an SMU, simply because I just can't average out as long as I can when I'm making the slower measurement. So again, there's definitely trade-offs you have to think about when you go from the SMU world to the fast pulse measurement world. And if you haven't figured it out already from what I said, SMUs really cannot perform what I would call ultra-fast measurements. In this case, you really need some different type of module. So this slide kind of shows the comparison of the different modules, some of the different modules we have. But again, a standard SMU can maybe go down to 500 microsecond pulse width, timing resolution maybe 100 microseconds. We do have another module, the medium current SMU, which can be a little faster for pulsing, has some limitations. It's better, but it's still not really going to get you down to that ultra fast level. We do have another module I'll talk about more later as well, which is the WGFMU, stands for Waveform Generator Fast Measurement Unit. I know it's a little bit of a mouthful, but it actually can do like 100 nanosecond pulses. Not as high a voltage or current, but it can do very fast sampling and has a minimum sampling rate of 5 nanoseconds. So again, a tool like that or a module like that is what you really need if you want to go and have to make ultra fast measurements. By the way, I will explain also why you want to make ultra fast measurements in a little bit. So you might actually ask the question, which is reasonable to ask. For a long time, we seem to get along fine with just making measurements with SMUs or curve tracers or whatever, and we didn't really have to make ultra-fast measurements on our devices to get enough data to make them function properly. So why has that suddenly become important? Why do people suddenly care about this? And one of the main, well, there's a lot of different reasons, but I could summarize it, I guess, in 2 main points. First one is that, of course, the device geometries have gotten smaller and smaller and smaller and smaller. And as that's happened, some of the effects that didn't really matter when you had large devices have suddenly become to really start impacting what the device does or how it behaves. The other one is the voltage levels that we had. Remember, in the old days, we used to have 5 volts and 3.3. The voltage levels keep going down, and as the voltage levels go down, that also means your margins go down, so that effects before that might not have had any kind of effect on the circuit operation, because those margins have gotten so much smaller, suddenly now they can actually have a big impact. So again, things like, I'll talk about NBTI, PBTI, I'll explain what that is in a minute. They actually have a big impact now because the margins are smaller. In some cases, also people are trying different types of materials, high-K gate dielectrics, even people who are playing around with silicon on insulator for a while. Those basically don't behave quite the same way as some of the older technologies. There's also something called random telegraph noise. That actually can be important because, again, remember I said the margins have decreased. RTN can actually have an impact on the stability of SRAM cells. Now, SRAM cells are critical for basically a lot of stuff in semiconductors, but primarily cache memory, like first level cache memory. Anything that does processing has got SRAM in it. And if you have unstable SRAM cells or SRAM cells that can occasionally flip bits when you don't want them to, or then basically that is a big problem. So understanding that is very important. And that's become a problem as, again, devices have shrunk and margins have shrunk. Also, our stuff today tends to operate a lot hotter than it used to operate, dissipating more power, it's more dense. And that actually makes all of these effects a lot worse than they used to be in the past. So the bottom line is in modern times, we really need some way to measure these parameters, which again requires, as I'll explain, why fast pulse measurement techniques. One thing that actually becomes very important if you want to make accurate pulse measurements, fast pulse measurements on semiconductor devices, especially on wafer, is actually how the devices are arranged or laid out on the actual wafer. So again, if you don't have a good structure design to start off with, you can have the best measurement equipment in the world, but you're still going to have issues, as I'll show you in a little bit, because of the way you've designed the structure. And that is unfortunate. So part of the reason I want to point that out now is, again, if you are going to be designing test devices in the future, you want to make sure that you keep some of these best practices in mind as you're going forward, so that you don't create a lot of pain for yourself later on when you actually try to make the measurements, and can't, simply because the structure is causing ringing and things like that you can't eliminate. So one thing people don't sometimes think about when they think about their pulses and how fast the pulse rises, how clean a pulse they can get, is that you have to go back to your basics on like Fourier analysis, things like that. And remember that a square wave is actually the superposition of a bunch of sine waves, right? The odd harmonics. So basically, you got all these higher level harmonics, and what those actually do is they determine the sharpness of the rise time on your waveform. So if you don't have those higher harmonics, you start getting a more and more distorted waveform, because again, think about it. If I only had the first harmonic, I'd have a sine wave. Well, that's got a terrible rise time. As I add in the additional harmonics, I get a much better square shape wave. So even though you might not think sometimes how much bandwidth you need, to get like a 10 nanosecond pulse, 2 nanosecond edges, in order to have enough bandwidth to have all the higher harmonics necessary to get that sharp rise time, you might actually have to have almost a gigahertz of bandwidth. So it is important that you keep this in mind in terms of how much bandwidth I actually need in my system if I'm going to try to get good, accurate pulses. So on this slide here, I'm starting off showing kind of a typical arrangement. A lot of times people will lay out a MOSFET with a gate drain source and substrate arrangement. And again, I'm showing coaxial probes being used because for high-speed measurements, we're basically using coaxial, not triaxial. This is not an SMU measurement. But notice that because of the long signal paths that some of the signals have to go through, it's not 50 ohm, by the way. Nothing is going to be 50 ohm on your wafer. So you're going to get a lot of distortions. And if you try to apply a pulse, a very fast pulse, you start getting a lot of ringing and reflections and things like that. So this kind of arrangement probably is only good till around 200 nanoseconds. And again, regardless of how good your measurement equipment is, if your pads and devices laid out like this, you're probably not going to get a very, you're not going to be able to go to a lower pulse level. Now notice here, I've actually made a very subtle arrangement, or subtle change, I should say, to the pads and how I arrange my device on the wafer. Basically positioning the drain to source as shown, so that there's a very short signal path going as I pump signal into the drain, going to the source, and also gate to substrate has a nice clean signal path. So very minor change, not hard to do. I could have, you can easily do this in the layout stage, but now I'm actually can get down to 100 nanoseconds or maybe even better than that because I don't have such large signal paths going through when I'm actually trying to make my measurements. So again, just a slight change sometimes in the way you've laid out your pads can cause a major change in the results that you get when you're actually trying to make a very fast pulsed measurement. Now, again, if you want to get the absolute best performance, you really need to use probably RF type probes and use what's called a ground signal ground type arrangement, where I've got the ground pad as shown here connected up, and then I also keep the same sort of short signal paths as I showed on the previous slide through my DUT. And again, by doing this type of arrangement, I can get down easily to maybe 10 nanoseconds or sometimes even a little bit better on my pulse widths. But again, I guess as I'll explain, the downside of this is, of course, you basically are, in this case, using RF probes, which can be, again, very expensive. And it does limit you to some extent because you have to use a very specified fixed pad configuration if you want to go like this. But I guess in general, I'd say for most people, the one I showed previously probably is okay. But again, it depends on what you're trying to do and what kind of pulse widths you're trying to create on your for your measurements. Another thing to keep in mind if you're making high-speed measurements is that you want to keep the signal paths clean. So if you actually do have some sort of control signals going to your DUT, and you want to keep those basically perpendicular as shown here to the signal path. So you want to keep the signal path flowing straight, not having any of these control signals in the way, and put any other sort of control or biasing signals like that. You want to have them going perpendicular to them. And again, the picture in the upper right of this slide shows kind of how you would do that on an actual wafer. But again, try to keep the probes separated to eliminate crosstalk, and all grounds, make sure they're connected together so that you have a nice solid grounding when you're actually making these high-speed measurements. So if you're using DC probes instead of RF probes, which again, I think most people probably are because the cost factor of RF probes is pretty high, it doesn't mean you can't make pulsed or high-speed measurements. You can still do it, but you do need to have the proper sort of setup or cabling. So here I'm just showing, we actually do make a cable set that you can purchase that allows you to connect your probes up together as shown here so that all of the correct return paths for the current are taken care of, so you don't get these strange reflections, things like that. And again, if you're using it, I'll explain what the WGFMU module is in a little bit, but it's probably okay if you want to use it for that type of measurement, maybe in the 100 nanosecond or slightly faster pulse width as well. And it does give you the ability to have, more flexible pad layouts. The downsides, I guess, would again be that going below 100 nanoseconds is maybe a little problematic. It also does create a little bit of mechanical tension on the probes. And what do I mean by that? Well, you connect these probes together, they're really close together, and you've got these little cables. You can actually sometimes get this problem where the cables will jump. You pick them up and the probe tips jump a little bit from the mechanical tension. And of course, not all prober companies necessarily support this. So again, you have to check and see if your prober company does support these types of cables. Again, if you want to make really clean RF measurements, and of course, in parametric tests, we're not oftentimes making true RF measurements, but if you want to make really clean pulsed measurements, using an RF probe will give you the best results. That's definitely clear, because these things are designed to go much higher, much faster than, of course, we're doing anything in parametric test. So they got plenty of bandwidth. You can't misconnect them. the disadvantages, again, are cost and the fixed pad layout. So again, it depends what you're doing and what you need to do. When I say cost, I'm not kidding. These probe tips, I think, cost around, last time I looked, at least $1,000 per probe tip. So you definitely want to be careful with them and make sure that you don't damage them because they're very expensive probe tips. But again, it does add a lot of cost to the system. And as I said, it's not usually necessary for parametric tests most of the time to use RF probes. It's just that I'm just pointing out you can do it, and they do give probably the best results. But again, they have a lot of limitations and cost issues. There's another important thing to think about if you're making pulse measurements, fast pulse measurements, particularly on a wafer prober. Gets back to that issue I talked about earlier in this. Remember that wafer chuck becomes part of the measurement. It becomes part of your measurement setup. And it, again, as I said, it's a huge capacitor. And if you're trying, for example, to change that voltage on that chuck quickly, like a pulse. So in the bottom left there, you can see, what if I wanted to say have the pulse change, like I wanted to pulse the chuck? Well, it's not going to happen very quickly because, again, that's a huge capacitor and I'm trying to drive it. So yeah, I can have great measurement equipment, but it's not going to be able to drive such a huge capacitance and make that pulse fast enough. So again, you have to use your brain sometimes. Think about this. Well, like for example, alternative method, do I really need to pulse the chuck? Could I instead make the opposite type of pulse on the top of the chuck, or what my DUT rather, device? Because again, trying to pulse the chuck is just not going to happen. You can't do it. It's too big a capacitor. So don't even try to go there when you're doing this. But again, making fast pulse measurements, it is important that you keep in mind that chuck will become part of your measurement. So don't try to do anything strange like, doing pulsing of the substrate if it's connected to the chuck, because again, it's just not going to happen. That capacitance on that chuck is going to stop that from happening. Another thing that you really got to worry about that you don't really need to think about certainly as much if you're making IV or really even CV measurements is the contact resistance of the probe. So again, if you're probing a wafer, there's going to be a little bit of resistance from the probe to your DUT, and there's also some associated capacitance. Well, that's an RC circuit, so that can actually affect the how your pulsing behaves. So you don't want to have that resistance high. So again, you want to make sure that if you're making measurements and you're getting some weird results, you might want to lift the tips up, look at the inspect the tips under the microscope, and maybe clean them off or change the tip even if necessary, if it's got a lot of junk on it or it's gotten stuff on it, because any stuff that accumulates on that probe tip is basically could potentially increase the resistance to your DUT. And again, doesn't matter so much for the basic measurements, but if you're trying to make a high-speed pulse measurement, it can have a big impact on the kind of pulses that you can generate on your DUT for the reasons shown on this slide. Another factor you have to consider when you're making high-speed measurements or high-speed pulse measurements is the actual capacitance of the cable. And again, you might not wonder why that's important. Well, the thing is, there is some time it takes to charge that cable up and down if it's got a capacitance. So you can see on this slide here that actually almost get like a hysteresis type of effect between like a rising edge and a falling edge on my device, because that's it's going to be the ammeter doesn't really know the difference between current that's charging a cable and current that's going into your DUT. Now again, this is honestly, of course, not always an easy problem to fix. There's a couple of things you can try. Of course, again, the first thing is you always want to have your cables as short as possible, and that becomes very important for high-speed measurements, particularly to keep the cables as short as possible, because again, that will minimize the capacitance of the cable. Another thing you could also consider, and if you're doing this type of measurement, is why not make the measurement at the source, the current measurement at the source rather than at the drain, because again, that's usually at a pretty stable voltage, so I shouldn't be seeing this gigantic hysteresis charging, discharging effect on the cable if I measure at the source as opposed to measuring at the drain. So again, just keep this in mind also as another thing that can impact your measurements, again, if you're trying to make very fast, high-speed measurements. So this slide shows what I would kind of call the traditional, in quotes, solution for ultra-fast measurement that a lot of people have used, where they'll use some, SMUs or other types of instruments to bias the FET they want to measure to DC values. And what you do is you typically will just use a pulse generator and maybe apply a really fast pulse to the gate, and then you have a shunt resistor and an oscilloscope, and you're measuring the voltage drop across the shunt resistor to derive the current. And of course, the ID is the V voltage drop across the shunt divided by the shunt resistance value. And in theory, this can give you, you can measure the current going through the drain, right? But although this solution seems nice and clean and simple in theory, in practice, there's actually a lot of issues and a lot of limitations that you have to worry about. So what are some of the problems with the solution I just showed? Well, one of the main ones is accuracy. Again, the error of the instruments, it's actually summed together. So you have to add on those different errors of the instruments, and that's going to increase or decrease your accuracy. Again, basically, scope measurement resolution is not that great. Scopes are really good at time resolution, but not so great at like voltage resolution. They typically only have maybe 8 or 10 bits. The precision you need on your components is also very important. You have to have a very accurate calibrated shunt. Cabling needs to be carefully matched. You need to understand the cable delays in your cabling. And even things like connecting things together properly with a torque wrench to the proper torque, believe it or not, can have a big impact on the accuracy of the measurement. Basically, just creating the software to do this can also be a lot more difficult than most people think. We have created solutions like this in the past ourselves, but typically there were like literally man-months of engineering time put into them, because of course we actually did quite a thorough, I should say, job with it, but it actually is quite complicated. And again, remember that the VD applied to the transistor will vary with the drain current. So if you want to actually maintain, for example, a constant drain voltage while you're making some kind of a measurement, you have to have compensation routines put in for that. So that actually gets really complicated as well. So again, overall, this is actually quite a challenging thing to do with discrete components. So because of all those limitations with trying to use discrete components, we actually came up with a better solution. And a better solution is one that actually uses dedicated hardware for making the fast pulse measurements. And again, we have as I mentioned, the waveform generator fast measurement unit, or WGFMU module. And the basics of it are shown on this slide here. It has two channels per module. And then there's these things called the remote sense and switch units, which are actually what go out to the DUT. Because again, when you're making fast pulse measurements, you want to actually have the signals be, the cables going to the DUT be as short as possible. So you want to actually mount those RSU units on your prober as close to the DUT as you can. And again, the other things we can do, we can actually monitor, if you want to, you can monitor the waveforms through a buffered input to a scope. You can actually switch between an SMU and the WGFMU module as well if you want to using this. But it actually solves basically all the problems and issues that you have when trying to use discrete components to make, fast pulsed or just fast IV measurements. So this slide shows a fairly detailed summary of the capabilities of the WGFMU module. And again, the diagram here shows how each channel operates. And again, remember, there's two independent but synchronizable channels on each module, and that's actually very important because there are quite a few measurements that require two channels. So you only need to have one module to get both channels. And it's a really powerful module because again, it has not just a source unit, but it has what I call an arbitrary linear waveform generator. So that actually allows you to define any kind of arbitrary waveform you really want to apply to your DUT. It could be a pulse, but it could also be a much more complicated waveform. And it could be a fairly long duration as well. Also important to note is there's actually two modes of operation. One is the pulse generator mode, where it operates more like a traditional pulse generator. There's a 50 ohm output impedance on the output. The other one is a fast IV mode, there actually isn't any inherent output resistance or output impedance. So it actually is operating a little more like an SMU. Also important in the fast IV mode, notice it can measure not just voltage, but it can also measure current, and that's really important. So again, this one, and also, by the way, it's pretty accurate. It actually has a 14-bit ADC, so you get a pretty decent measurement data out of it, and it can take a lot of samples, a lot of points. It can sample very quickly, and this particular module again solves pretty much all the issues you have using discrete components to do a similar type of measurement. So negative bias temperature instability is one of the key things that we want to use our fast pulsed and fast IV measurement capability to characterize. And again, it's one of those phenomena that is, came of importance relatively recently, mainly because, again, margins have shrunk down, devices are hotter, and it's just causing problems now that we never saw in the past. Basically, it's a shift in the V threshold, which creates a reduction of the on current when the device is negatively biased. The important thing about this is it actually does, it's dynamic. So it's believed to be caused by electron trapping and detrapping and certain charge trapping. So it's not a permanent change to the transistor, but it actually is difficult to measure because the problem is you apply a stress to the transistor and it will start to degrade with this phenomena. But the problem is when you remove the stress from the transistor, it actually recovers fairly quickly. So you actually have to be able to remove the stress and make a measurement very fast on the transistor and maybe even return it into stress again, without having any glitching occurring, if you want to understand how this is actually going to behave in a real circuit. And again, remember, in a real circuit, I'm never removing the stress. It's always under stress and the behavior will degrade. But but the difficulty is not that, or I should say the difficulty in this is that it is a difficult parameter to measure because of the need to go from stress to measure so quickly and so fast. And again, I'm talking nanoseconds here. So this graph shows the percentage change of ID, a delta ID, versus accumulated stress time for different types of stress applied to a device. And again, the purpose of this graph is simply to show that the change you get is very strongly dependent on the type of stress you apply. Again, if I apply a constant DC stress, I get obviously the most extreme sort of degradation in the drain current that I see. A lighter duty cycle, maybe only cycling 50% or 25% of the time, gives me, of course, less change in the drain current. Why is this important, though? Well, a part of the issue here is we want to test our devices realistically. We want to have them measured under sort of normal operating conditions. And obviously, in normal conditions in a circuit, the transistor is probably not biased 100 or negatively biased 100% of the time. There's things switching back and forth. So, it's more realistic to give it some sort of duty cycle, 50% or something like that. If I can't do that in my testing, then I probably am going to over design my circuitry more than I have to, which is not a good thing necessarily because you're going to have additional costs probably associated with that as well. So we want to have a testing technique that can bias the device realistically. The WGFMU module can do fast NBTI or PBTI very easily. And again, because it has that arbitrary waveform generation capability, I can generate different types of stress. I can generate a DC stress. I can also generate an AC stress waveform very quickly, very easily. And I can also easily go from stressing my device to making a measurement. Now, it could be a simple spot measurement, as shown in the top there, top right of my diagram. I can even do a sweep measurement if I wanted to, for example, do a very quick sweep measurement from stress and go right back into stress without having any kind of glitching. So my device definitely keeps its stress and it's not going to relax and go back to its normal state. It can do very fast sampling, less than a microsecond, and it's got a lot better noise capabilities than SMUs, of course, have. So again, very good solution, very good tool for doing these types of fast measurements. The software that runs on the B1500 is called Easy Expert, And it has these things called application tests, which you can see here on this slide. And just point out in passing that we do have a BTI application test built in that can use the WGFMU module. So again, this is just one example of the many tests we have. This one can actually do perform a user supplied or user defined AC stress on a device, and then periodically we'll check it to see how much the ID has changed. So again, you can actually do this without having to do any kind of programming or anything like that, which is very nice. Again, if you want to do this type of testing. So I talked about NBTI, PBTI, and that's important, of course, and that's one reason we do high-speed testing. Another one that's become important recently is something called random telegraph noise. And basically, this is another case where as MOSFET geometries have shrunk and also voltages have shrunk, it actually starts creating problems that never existed in the past. RTN is again believed to be caused by charge trapping and detrapping. And if it does occur, it generally tends to be the most dominant source of noise that you're going to see. Something called active pixel sensors or CMOS image sensors, they're actually very sensitive to RTN. If it happens, it'll generate what are called erroneous white spots in areas that should be dark. But quite honestly, in my experience in the Americas region, I don't have any customers like that. So I didn't have anybody asking about RTN noise until more recently when it actually started to affect SRAM cell stability. Because again, as everything has started to shrink, there are instances where random telegraph noise can actually start making the SRAM cells unstable. And of course, again, that's not something you want because that makes your cache memory unstable. So we have had a number of customers who've used used our equipment to measure this noise, I think, just for those types of purposes. So before I talk about random telegraph noise, let me back up a second and talk about what is a random telegraph signal. So this is essentially just a random process that has the following two properties. Basically, it's binary. It has two values, plus or minus 1. And if you were to look at it, the number of times that the function is going to cross 0 in any instant interval of time, defined by 0 and t, is described by a Poisson process. Okay, so it's just kind of a stochastic process that's it comes basically from probability theory, things like that. Now the issue is that we actually see something like this in our semiconductor devices. Of course, that's why we talk about random telegraph noise. So what's the actual technique for measuring random telegraph noise? It's actually fairly straightforward, fairly simple. And again, this gets back to why it's important to have a module like the WGFMU module with 2 channels on it, because you actually need to stress and monitor both the gate and drain of a transistor. Actually, generally stressing is probably not the right word. You're applying a bias to it, you're turning it on. But what you're not really pulsing it in this case. All you're doing is measuring the drain current, but you have to measure the drain current very fast, because if there's any RTN noise occurring on the drain, it's going to be occurring in like nanosecond time frame. So you have to have something that can record this and measure, thousands or hundreds of thousands of points over varying time periods. Let me point out a couple other things. I have actually measured this on wafers, and when we say it's a random telegraph noise, it is truly random. You typically don't see it on every device. When I first measured it, I think I measured almost 10 devices before I even saw this thing happening on a device. And not only does it not occur, occurs maybe only rarely on devices, it also is strongly dependent on the gate to source biasing. So sometimes just changing the gate to source bias by maybe 100 millivolts can actually make the phenomena appear or disappear. So ideally, the easiest way to really find this or determine this on your process is you have a wafer, and what you really want to do is you want to step across the wafer. So you want to touch down on a device, apply several different gate to source biases, make a whole bunch of measurements at each bias point, and then go to the next device and do the same process. And you have to go across the entire wafer. So it's a tedious, long process if you really want to find out how much of this RTN noise is actually occurring on your devices, but that is really the best or the only way you can probably do it. Because again, just trying to randomly pick a device and looking at it probably isn't, good chances are you won't see this at all. So we have some software we supply that allow you to do the RTN, not just measurement, but also some analysis on it. So I'm not going to go into the details here of that software. I don't really have time, but I wanted to kind of just show you what it looks like. So again, this was a measurement made on a device, and you can see very clearly here, very distinctive RTN noise signature here. And this is basically generally kind of stuff you'll see, not always. This one's actually pretty pronounced, I'll be honest. But this is what RTN looks like. So if you see it, it typically is very distinctive, and you'll know when you see it. This one also does actually have some other capabilities, like it can plot out things like histogram and other things like that. So you can kind of see the distribution of the noise and so forth. But basically, this is what it actually looks like on a device. So again, it does require sometimes a lot of samples. This one was 20,000 samples. And basically, you can see how fast we're sampling it here. So again, this is something that requires a very fast sampling capability, and something that you can't do with an SMU that you can only do with something like the WGFMU module. Now this slide shows another device, another process we measured with the WGFMU module. And I wanted to show it because it just kind of emphasizes that not everything is as stark or as clear as I showed on the previous slide. This measurement you can see here, initially you look at this and it really doesn't even look like there's RTN. There is like a lot of noise that we're capturing, but it's not so clear we have RTN. But if you go in and take this area here and expand it out as shown here, yeah, then you can actually see, well, once I expand it out, okay, I can clearly see that I actually am having some RTN noise occurring on this device. So just to point out, sometimes the appearance of this can be a little more subtle. It really depends on the process and device, but it is something that is definitely important to understand. Again, it's become important, as I said, primarily because if this is severe enough, you can actually have issues with cell stability and things like SRAM. So again, it's pretty important, and most major semiconductor manufacturers do some measurement on this of some sort. On this next slide, I'm going to give you a, I think, very valuable resource if you want to get more information on anything I've talked about today. Before I move on to the question and answer session here at the end, just wanted to point out that everything I talked about today is actually covered in our parametric measurement handbook shown here on this slide. It's 277 pages. It's now in its 4th edition. So you can very easily download it from the link shown here. And again, if you want to find out more about pretty much anything I talked about today, I recommend that you download it and take a look at it. Because again, I think it's just a really good reference source for general parametric information. Okay, that concludes this second session. So let's go ahead and move on to the questions and answers.
Yes, thank you so much for the excellent talk, Alan. And yes, now we are open for questions. And people that are attending via YouTube, please, you can type your questions on the chat. I will bring them here to the people, to the experts on Zoom. Thank you. So please, people on Zoom can just open your microphone and camera and ask the questions. Let me take a look if there's something. Yes, maybe by people will ask questions soon. So, Alan, while the others do not ask, let me ask a question. If you could comment if there is a trade-off between resolution, I mean, the number of bits you get, and the speed, the sampling rates. And for instance, you are using the SMUs or other sources, if they automatically adjust the resolution, the number of bits that you are using based on the speed, on the sampling rate, if there is something done automatically there, or if it has to be adjusted by the user.
Oh, Yeah, so I'm trying to think how to answer that question. It's a kind of it's a simple question, but it's not a simple answer. So yeah, when you're using an SMU, again, well, okay, any measurement. I didn't get into that, I guess, so much on the WGFMU as well. So I guess when I talked about SMUs, remember I said there's different types of ranging that you can have, like there's auto and limited and fixed ranging. The WGFMU, so of course the number of bits you get, the resolution depends on the range you're measuring in. Now SMUs, you can't have it automatically like auto range down to get the maximum resolution, but it takes a long time when you do that. So if you're SMUs, you can do that kind of automatically as long as you don't care about the speed of the measurement. When you're making a fast pulsed measurement with the WGFMU module, something like that, you actually have to pick, it doesn't have auto ranging. So you have to pick a measurement range kind of to make the measurement in. So you have to kind of be aware of what kind of, or where you expect the measurement to be. And then that will, of course, determine to some extent the resolution number of bits you get. Now, you do get pretty good, again, you get pretty good resolution with the WGFMU module in terms of bits. But again, if you have widely varying signals so that you have to pick a higher range to catch the higher signals, you lose a little bit at the lower end. So yeah, I mean, there's a lot of trade-offs. I mean, making the fast pulse measurements is a lot trickier, obviously, than using an SMU where things can kind of be done automatically. So you have to, I guess, do a lot more thinking about what you're measuring. I should say, maybe that's the best way to think about or say it. A lot more thinking about what you're measuring with the WGFMU or a fast pulse measurement. It is a lot more difficult to get the bits. I don't know if that answers the question, but
yes.
Yeah,
And
I'd just
maybe
like to add a point to what Alan mentioned. So in terms of like the DC measurement with the SMU, one of the things that we could choose, or the B1500A offers, is the option to choose between a high resolution SMU and a high speed SMU. So if you want that higher resolution, you can choose the higher resolution SMU, which takes a little bit longer for the measurement. But again, if that's a little bit of flexibility that the solution offers when it comes to higher speed versus higher resolution.
Yes, and also make a measurement before. I mean, a trial and error in the sense that you make some measurements to see what the range you need. I mean, what is the order of magnitude of your signals that you are measuring, so that you use the proper range in the SMUs. I think to avoid that you use too large range, or the signal is small compared to the range you are, or if it saturates at the end. Yeah, I think, in my opinion, it answered quite well the question. Let me see. I think we have a question. No. You can, if you have a question, you can just open. Let me look at YouTube quickly if there is some question on YouTube.
Is there a ready solution for measuring MOSFET gate capacitances while having drain current flowing? Trying to think about that one.
Yeah, we don't well, we have ISTs, but we don't necessarily turn on the device and let the current flow during capacitance measurement.
Yeah, that's hard to do. Yeah.
Yeah.
Even on power. Or yeah. Well, go ahead. You want to answer it, Tasia? Yeah.
No. Yeah, I was just thinking, like, okay, it's not possible with the B1500s. But I'm thinking you could do other measurements, like maybe use a network analyzer and a bias T there. You could, one thing that you could do is calculate as parameters of your MOSFET and then extract the capacitance out of that as parameters. So there is a way you could do on state as parameter measurements. It's not quite with the B1500. That's a different solution.
Yeah,
so,
right.
The answer is, yeah, it is available, but again, it depends upon what is the on-state current. Is it a few milliamps? Is it amperes? That determines if it is feasible for your particular application or not.
Yeah, small signal would be pretty easy. I mean, obviously on a power device, yeah, I don't know how we would possibly do that because it's really hard to, well, you can't bias a power device to high voltage and then have current flowing at the same time very easily and measure capacitance. We don't normally, that's not something normally people would measure, of course, but yeah. Oh, so I think they're asking if it's possible with the B1500. Not with, yeah, we can't. So as Tasia said, maybe you could do something with if you set it up with a network analyzer or something that has parameter measurements, but you can't do you can't have the transistor on. We don't measure the transistor on when we're measuring the capacitances typically with the B1500. Yeah.
Okay. There are more questions. I have also one comment. If you could comment about the amount of memory available, especially in equipment for measuring transient signals, so just RTM. What equipment would you recommend if you need a lot of memory in the sense that you want to measure, to analyze a long time series with a lot of measurement points, that you need a large amount of memory? What would be the best equipment for this?
Well, yeah, so I guess I kind of so like to measure RTM, what most customers do actually who want to measure this using our equipment is they actually most of them write their own software, have some sort of software running on a PC to control. So they control the B1500 sort of remotely from the PC. And part of the reason is that, yeah, I mean, it's got the WGFMU has a relatively large memory buffer. I don't know. I think it can hold millions of points if I remember right.
I think it's like 4 million samples.
4 million points, right? Yeah. But that can fill up pretty quickly if you're sampling. Again, the procedure is to, the best procedure again is to step across a wafer and take multiple measurements on multiple devices. So typically you need to store that data into a PC. So you have to offload it. So you make the measurements, the data gets stored in the WGFMU buffer, but you have to transfer that data onto a PC and save it there. So the buffer itself, so I guess to answer your question, it's got a pretty big buffer, 4 million points, but to actually do across a wafer, you're going to have to basically take the measurements on each device and store them, probably in something else. And then and later on, you're going to go back and analyze that data as you stepped across a wafer. Again, it doesn't, the phenomenon of RTN doesn't appear, it's random usually on most processes. It doesn't always happen on all devices. It also, as I said, it's really dependent on the biasing. So, it's surprising, but you can just change the gate to source, or gate to source biasing a little bit, and it can appear or disappear. So it is a tricky thing to measure.
Yes.
Yeah, it's a tricky thing to measure.
Yes, thank you. I was thinking exactly about that you can do one long measurement and one device, but sometimes I think it's important that you can make a long measurement with many points, so that if you are interested in, you can even make a Fourier transform to see how it is in the frequency domain, or you can do some statistical analysis. And as you said, sometimes you don't know if the time constants are be fast or slow. So if you are doing it automatically, so that can do in one device a long measurement, and of course, million of points is very good, and then store it into the computer, and then jump to the other device. But I think, sometimes it may be important that for the single measurement on a single device, you can measure a long time series, a lot of points, and yes, providing million of points is, that's great. Yes, thank you for the answer. Yes. I think that was what you did mean, right, Alan?
Yes, correct. Yeah.
Thank you.
Correct.
Thank you. Let me see if there's some question on YouTube. I'm going to switch my window here. Yes. I think there are more questions, people. Yes, okay. So I think there are no more questions. And so thank you very much for the great talk. And yes, and people don't forget to fill out the form, so then we'll have access to the slides and other supporting documents. Don't forget to fill out the form. You have the link both in YouTube and here in Zoom. You have the link there. Please fill out the form there to get further information and the slides of this great presentation. So thank you very much. Really, thank you very much for the presentation. I did learn a lot. Thank you.
Oh, no, good. You're welcome. It's my pleasure. Thank you.
Thank you.
Thank you all.
So Rafael, I don't know if you want to finish the presentation, tell something about the other. I think at 11 we have the opening session, right? At 11 o'clock. So in a few minutes.
It's actually 11:10. Okay.
At 11:10. Okay.
Yeah, we'll be back at 11:10. We'll do a short break now. So please stay here for the opening session, and then we will continue with the conference. Thank you, everyone.
Yes, thank you, everyone. So we have a 15-minute break, and then we have the opening session of the conference. Thank you so much, everybody, for listening, especially Alan. Thanks for the great talk.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes, but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So, get a taste of our work. Appreciate the little things, and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.
You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Tools and outfits. They're practical, give us comfort, create unity. They're part of an identity. At IMEC, we've got tools and outfits too. They help us do our jobs. But underneath them, there's us. And we perform science. Mathematical and accurate data, together with powerful gray matter that thinks out of the box, is the foundation for our creations. And the accumulation of digitization for the continuation of our population